Well, it's a data crunching exercise in very, very close collaboration with someone we've heard a lot in these last 3 talks, Jim Anderson. We were meeting very regularly with Jim. We've known Jim from a long time. And every month we have our coordination meetings, troubleshoot what we think is not quite going right and things of that sort. And then in between, we meet with his staff, Emily, and various folks, which we'll acknowledge at the end. Yes, this has been a really fun activity. Prior to this, we started, as you'll see, working with actually our barley breeder, Kevin Smith. But so it's actually three of us that are coordinating this. We've got myself, again, a computational geneticist. We've got actually an applied economist, Yuan Chai, and Jim. And the main focus of this, and hence my question to George just a minute ago, was really understanding that interaction of genetics by environment is critical. I mean, with pretty much every one of these traits that we measure, some more than others, for sure. And that's, I think, in the next slide. Yep. It's really the thing we all want to know is, we might know how our variety performs in maybe our perfect conditions, but nature is anything but, and we've seen that with the drought these last 2 years, that we could create a prediction model that say, oh, I can predict this, no problem, as long as you train that model and think about it like over the years of normal weather, whatever the heck that is these days. And then suddenly you get hit with a whammy, like 2 years of drought, and all bets are off. If you've trained it on something that you've never seen before, every model is going to fail. Okay, there's no model that's going to if it's an extreme of conditions. And please keep that in mind. When someone tries to sell you a model and they say, oh, this will work no matter what, that's not true, okay? You have to take it within context. But the more time, the more different experiences you have to train a model, the better you're going to do. So there are things that we know to be highly conditional on the environment that we're growing it in, such as yield itself, which we're all interested in, protein content, and several other characteristics. And so we wanted to say, can we leverage, since now there's a wealth of data out there. There's tons of data of sampling that's been done for soil all throughout the US and actually the world. There's a lot of weather data. Every 15-minute intervals you can collect weather data of all sorts of different kinds throughout the world. Can we use that information to inform our models, plus the genetics? Because really that interplay of G by E. Oh, I was supposed to mention what DEMS was. It's just, our group just focuses on the interplay of genetics, G, by environment, B, by farmer management, M, and socioeconomics. GEMS just stands for, we take it all into consideration when we do our modeling. Okay? So, in considering, think about the breeding cycle. I mean, for wheat, it's at the University of Minnesota in Jim's program, it's 9 years. So when you first have the conception, that first cross, and you're thinking about, okay, I want to project 9 years out for what I want to target. Think about the things that are changing in that 9 years. It used to be climate was about a 30-year thing. Now, really, honestly, climate's changing at about a 10-year cycle, okay? So already that 9 years, we're breeding for an environment that really is going to be different. And secondarily, now think about how the pests invasion and things like that are affected by climate. It gets warmer, different insects are coming in, different fungi, different bacteria are invading. Think about the market forces, how they're changing. That's faster than 9 years. That's, the things that people care about is changing. So all those things you actually have to think about in your predictive science. And if we can shrink this breeding cycle, that in itself is an achievement. And so one of the things, our first direct thing we're pretty sure we can do with our predictive science and talking with Jim, is there's 2 places we can target in this breeding cycle that we can shrink that cycle. And first is this place in red here, in his pre-yield trials effectively, when he's got like 3,000 lines, and normally he has to try to phenotype them all to say which ones should be ones that I should use next. Well, what if you could just use genotype plus the weather and soil information, and you could predict what those phenotypes were with great accuracy? You wouldn't have to do so many lines. You could do far fewer and pick the winners and then move on next. Shave off a year at least of that program. Likewise, when you're in your advanced yield trials, you're picking the varieties for the next cycle. You could also, instead of taking 2 years, you could shrink that down to 1 year and shave 2 years off and have 2 more years of viability and get it out to market 2 years earlier. That's our goal, really, with what we're trying to do with this study. Okay, We published a paper in Crop Science last year. We think it was a pretty cool paper, and we actually looked at, a lot of folks try to predict yield. We simultaneously were predicting a lot of different traits. I mean, in this particular case, we're looking at percent protein, we're looking at the heading date, plant height, and test weight. But in principle, the methodology that the multi-regression model that we were using can use whatever you happen to be interested in. And in wheat, there's a variety of things that Jim would like to target. Fusarium head blight, looking at baking quality, looking at stalk stiffness, and various other things that we care about. And these are the things we want to simultaneously try to make predictions for. In this particular barley trial, when we left various ones out of the training and we tried to predict what they would be when they were never in the training set, we were between 0.87 and 0.95% accuracy, really, with all of these. So what are we trying to do for wheat? Okay? Jim and his staff have been heavily at work amassing like a database full of lots of information that they've had over the years. All right? And they had a bunch of students come in for this project, and it was great. They went back and dug 10 years back. So we've got data for 15 different sites in 10 years for a lot of different phenotypes that they've screened. And we, of course, have data for the weather back to 30 years or so. So we have that. We have that covered. Genotyping, they've got information for 135 varieties. Some of these are commercial, some of these are Jim's lines, and they've gotten permission to use those as well. Plus, there's several more that they're still waiting for information from the commercial companies, basically to get permission to use them. And of course, we have the weather and soils data. So, what our approach is we really want to, well, as I said, to kind of save time in the breeding cycle and shave off time is our initial goal. We want to actually create some tools first for breeders. At this point, I mean, given the funding that we have at this stage, we can actually create some breeders that ask the question of, hey, what varieties could I grow in this location in Minnesota? Or turn it around and say, what locations could this variety be grown, all right, and grown well, according to, and then just list the phenotypes I care about, okay? Down the line, and I say likely in the next funding cycle, if that were possible, we would like to create tools for growers. There's only two reasons why we don't have that included in this particular funding cycle, and that's simply because the cost would exceed what it is. Building user-friendly tools as opposed to some R programs to do some R programming is much more, takes a lot more effort. And secondarily, we don't think that we'd feel comfortable yet at this stage. This is a little bit exploratory. We know it worked for barley, but we never used it for another crop yet at this point. We're exploring, we're seeing a lot of space. And you'll see in a subsequent slide, there's input we need from this community. There's input that we could get from the growers. We certainly can get some from Jim to really make sure that we trust the results that are coming out there. Because we're not the kind of, even though we do computational stuff, we've always worked with actual people in the field. We don't, it has to be a partnership if you're going to get something real in the end. Otherwise, people can just bake things in the sky and say, hey, look, this will work. And that really doesn't. It doesn't work that way. So we've done a lot of genotyping in this cycle. Jim's group basically did really good. Lots of times, you get maybe 4,000, 5,000 markers. That's all we had for barley per variety. But here we've got, the sequencing was really good. It got 11,600 markers spread pretty evenly across all three subgenomes, which is really nice. We had fewer on the D genome, and that's actually very typical from what's happened in the past. It just, you just don't get as many markers on there. But it's nicely spread across nearly every one of the chromosomes. So that was really good. Very encouraging to see that. For this type of analysis, you get plenty of information from even 4,000 or 5,000, so 11,000 is going to be like, bonanza. So, there. So the first step in the procedure is first to actually look with respect to each of the phenotypes that we care about to try to see, hey, what are the agroecologies that are actually similar to each other based on that? Now, this is fraught full of potential problems, and this is one place where input from the farmers and the breeders actually has to come into play, because there's things that we can play with. Anyone that says, oh, I'm going to generate this graph and that's it, they're somehow either not understanding the way that this stuff works, or they're pulling the wool over your eyes, because behind a map like this comes lots of decisions that have to be made. Those decisions statistically have to be made, and it can be a little bit arbitrary. And so I'm just, I like to, some people, I just like to be completely honest with you of these things. And that's why we need to kind of talk. We need to sit down and say, does this map make sense? Scientifically, the parameters we used seem the most defensible from a data science point of view, but that data science point of view doesn't necessarily mean that that's real. Okay, these are actually color coded from latitude, basically from top to bottom of the trial locations that we have. What regions are most similar if you had to pick any of those to that particular region? So in this particular case, you can see Wasika, the yellow, is actually similar to where Wasika is, but also up to some areas up that venture up north. So, or something louder. Okay, but we'll talk a little bit more of that in just a slide in a second here. So just say what I just mentioned. Here's some of the things that go into it. When I'm trying to say what's similar to, I need, I have a 40 or 50 dimensional vector, and that's kind of an abstract concept. Think of like 40 weather variables and 10 soil variables. And each has a value. Every time I make a planting and observation, each has a variable. And when I say, oh, with respect to yield, which one of those is similar to another one, I'm doing just a standard Pearson correlation, which we saw a lot of graphs that people, or I could do a Spearman where I take the ranks instead of the actual values, or I could do the cosine simulation, which has a cosine similarity. There's so many different ways I could do just similar to. And then I have to choose features. So there's a special method called lasso, which allows me to look at the variability of all my variables together and say, guess what? These 5 variables affect grain yield, and all the rest of them could just be zeroed out because they're not important at all. That's one method. Or I could start adding one at a time and see if I add one variable, does that change the root mean squared change from the average? And I add another variable, does that change it? Nope, throw it out. And then I get variables that way. There's just so many different methods. And do they give the same map that I showed you? Well, there's subtle differences to those maps, actually. And those subtle differences, you might be able to say, hey, there's no way those 2 locations are similar. But this is a critical first step for me then to predict actual values. And that's why I want to pause here, convene a meeting. We'll try some other things as well in parallel, but convene a meeting and actually discuss with this community. So anyway, we'll train the models on the 10 years of the wheat locations. We'll make our predictions. And then Jim will use it in that first section where he's got his F5s. And then we'll see how it goes. In the future, so the next steps, i.e. if we were to get another grant, it would be great to get more data. Models are always better with actual more data because, maybe I only trained it for 4 years and then we missed that big drought and I never saw a drought in a condition. Guess what? I won't be able to predict there, okay? I mean, it's very important to have these experiences of different things to train the model so that it actually can recognize something in the range of what was seen. And of course, we know it's incredibly important to have useful tools for farmers. We want to do that. That's an incredible thing. So with this, I just want to thank all the folks that have contributed. So we've got, all across the board, the folks that have been directly working on this from day to day. And really thank our funders as well as the people who funded the work that led up to us having these tools to get here.
All right, that was a lot of information in a short time. Do you guys have any questions for Kevin? Anything that goes into the predictive modeling or kind of the grower-facing variety selection tool that we hope to have coming down the line?
I am curious about the map that you made. When you first made up the map, did you base that on, is that mostly soils or temperature, precipitation? What were sort of some of the parameters that went into that?
Yeah, so exactly, it's purely soil and weather variables, and it's all the ones you would know. There's 40 actual weather variables and about 10 soil variables. And then ultimately, though, to make this map, this was using lasso regression. It actually came down, I think, to just 5 variables that it picked everything else except can zero out. And again, not only when I wanted to talk with some folks, do those variables make sense to them? but also now does the map itself make sense? So I think Joachim might be in a good position with all the scouts to actually see a variety grown in multiple places, and does it actually seem to behave, or other people who have multiple experience with multiple places. So.